So as I first mentioned, we'll first look at the Baldwin-Lomax model. And I should also mention, if I haven't already, that this is the model we will program in your last computer project. So in the present computer project, you're trying to get your laminar flow solver running correctly. And you'll see how it is and why this model was so popular, because you could just take an existing Navier-Stokes CFD code and add in a viscosity term and a few ways to estimate the viscosity through a two-layer model and have a fully functional turbulent flow solver, which was used in practice. A few other interesting things about this model is it was really pushed forward and designed to overcome the limitations of the Cebeci-Smith model. So Cebeci-Smith model, especially in the United States and Western countries, was king. But there were some problems with it, and we'll see what those problems are that these authors identified in their paper and how they overcame some of these problems. So you might say, well, some of you might say, who are Baldwin and Lomax? Well, I spent a lot of time finding this portrait of the main author, the first author, Barrett Stone Baldwin Jr., and this, I think, is his U.S. uniform, because he served in the military, I think, through World War II. And down here is an older picture of Harvard Lomax, his boss, who was basically running that group at NASA Ames. So these are the two people the model are named after, and you'll see in the paper I handed out, that's, of course, the authors. There's a lot of information online about Lomax. He's well known in AIAA, the aerospace community, and so those are just some little tidbits. Here's the cover page, which I handed out, so we'll look at that later. And you can see originally it was part of the Air Force library, and sometimes it's fun to look at the kinds of computers they used, because these are pretty old by today's standards in 2022. But this is a picture of a similar machine that they used to benchmark it. CDC 7600. CDC is a computer company that's by itself no longer in existence. And some just interesting things. The computer that they were running their model on, which sucked it up, cost $5.1 million near the time of publication. And in this little box, which you could stand by, if you're about this high, it's about 120 miles of wire, and you can even see how much floating point performance it has and number of memory. So I think this is in the Computer History Museum I got this off of, which is a place in California you can go to see these types of machines for their preservation. Okay, so let's look at some of things about these people. Here's one quote from Baldwin and Lomax, their paper I pulled out to motivate the model. And it's kind of general, but they said there's a practical need in aeronautics as well as in other fields for the capability of calculating compressible, turbulent, separated flows. So this is something that was sort of lacking in the Cebeci-Smith model. This is also a local model. And they said, although progress may have been made toward developing a universal turbulence model for such calculations, that goal has yet been achieved. And in 2022, today, all these years later, we still don't have a true universal turbulence model that fits all flows in CFD to close the equations. So this is still an ongoing problem. The current numerical methods and available computers, like they just showed, they are capable of analyzing general 3D separated flows if a suitable model were in existence, meaning algebraic, and overcoming the limitations of Cebeci-Smith. Completely satisfactory methods for treating turbulence may not be available in the new future. In the meantime, it may be worthwhile to continue development of procedures for calculating complicated flows, that's a typo, based on simple empirical turbulence models. Results from algebraic turbulence models developed for use in 2 to 3-dimensional Navier-Stokes machines. Their original model is actually based on a paper by Steger to treat turbulence, and it may not be available in the near future. In the interim, it may be worthwhile to continue development of procedures for calculating complicated flows based on simple empirical turbulence models, meaning ones that can run on their $5 million computers at the time. So you can kind of put yourself in their shoes. The objective of this paper is to present results from an algebraic model developed for use in 2 and 3-dimensional Navier-Stokes machine codes, and that just means running on digital computers. So that was written in 1978. I suppose it's about 40, well, many years ago, 44 years ago. So let's just look at some major notes. This model was published in a conference paper in AIAA in 1978, and it was really made for boundary layers. And in boundary layers, like in the Cebeci-Smith model, you'll need boundary layer quantities like the displacement thickness, the boundary layer thickness, maybe shape factors if they're more complicated. And the edge velocity of the boundary layer may also be difficult to determine. And so that was one of the major problems with the Cebeci-Smith model, that I need to know something or find something about the solution while the model's running. And they wanted to eliminate all that. That's the major goal, and also improve predictions against separation and what have you. So the Cebeci-Smith model really failed for practical predictions. So this is really just sort of like a mathematical goal for separated flows and shocked flows. So in their paper, my view is they're writing that they want to overcome these limitations. But the people designing aircraft, like at the Douglas company where Cebeci and Smith were, they don't really care as much because they're in the business of making money and building aircraft. The people at NASA were a little more elegant, I would argue, and they wanted to have maybe a more elegant turbulence model that wasn't dependent on the solution before it was run. It's also a two-layer model, which you'll see in a second from my notes below. And we define the eddy viscosities very close to the Cebeci-Smith model. And here they are. We have an inner layer and outer layer. So just to remind you, that is something like we have a wall and there's a flow. This is UE, that's the edge of the boundary layer. And we have some boundary layer profile. That. And there's some intermediate region. And we'll call that sometimes M, because in the next model we'll use M to denote that region between the inner and outer layer. So this is inner and outer. And we, at length, I think, discussed why people divide these boundary layers in inner and outer layers, and for their viscosity models. So just like before, he'll say L mix squared, the inner eddy viscosity, and here's where the difference is, immediate difference, magnitude of vorticity. And you can check the units, you should be getting something like meters squared per second viscosity unit. Length scale, exactly the same. He had, so a constant, maybe it's around 0.41 times the distance to the wall, times 1 minus e to the negative y plus all over a naught. Let me write that out better. A naught plus. Okay. So you see, once again, there's like this little exponential factor. A plus goes as about 26 for partial p partial x is 0. Y plus is your non-dimensional distance from the wall, and y is just your distance from the wall in meters. So that's it. That's the inner model. So if you already have your Navier-Stokes boundary layer code, you could just divide the flow into an inner part, an outer part, and define two eddy viscosities. And somewhere in the middle, they're going to meet at location M. And you would just find that location where they cross over in your models and throw away the other part of the solution and have one eddy viscosity, which you add into mu. And we'll talk more about that when we introduce project 4. The outer layer is more complicated. We have like a constant alpha and C sub Cp times F wake times F cleb times Y, or Y max over C cleb. And you take the max value. And all these are just empirical functions which are very similar to before. Like there's a wake factor, and he developed his model for turbulent wakes and boundary layer, so you would just sort of get rid of this wake factor if you were in a boundary layer. This is your intermittency factor once again. Just like before, in the outer part of the boundary layer, we have intermittency gamma, right, which might vary between 0 and 1. And you have a bunch of closure coefficients. And these are what they are and what I believe he published, and we'll look at his paper in a few minutes. I've already mentioned that this is the intermittency factor, and he just took Cebeci-Smith's model and made a few little modifications. And we'll outline all these in the project in greater detail. Here's the definition of vorticity in three-dimensional flows, but these empirical constants were developed and calibrated for two-dimensional flows, like a turbulent boundary layer. So a few things, of course, if you're in 2D, you would have omega equals partial v partial x minus partial u. Minus partial u partial y. And so that's two-dimensional. And if you're in a boundary layer, you can just set omega equals partial u partial y because you're using the boundary layer approximations. Okay, so partial v partial x should vary very slowly when you're further down in a fully turbulent boundary layer. And so that's the basis of the model. Oh yeah, and then they do have like this little function you'll see appear in the paper, udef. That's just basically if you have a boundary layer, you might have a maximum and minimum velocity at two particular locations. So it may be that your velocity profile looks like this, where you have a max value and an edge value. So you'll see the model was, when we look at a few flows in the paper, you'll see that the model was trying to be generalized by changing little empirical coefficients and equations to handle cases when the flow separates, where there's like a flow reversal. So that means if I have, say, a boundary layer like this, here's the wall, and sometimes, because I have unfavorable pressure gradients, I might have a flow that comes up and has a separation bubble. So this might be a streamline. There's more flow. And it might go something like this. And this is like just a separation bubble. Other things that might happen, which are trying to be accounted for, are, say, interactions with shocks. So if you have a transonic airfoil, which a lot of aircraft fly in that regime today, you might have a shock here. And the flow is attached at the wall, but then it comes off the wall like this because of the shock, and then you'll have a turbulence separation. There's the flow down here. This is a airfoil. So it's developed to try and handle those cases some too, but not always well. The major development, which is simply getting away from all these problems of Cebeci-Smith. And I think like really this term here is a really good choice. Why? Because away from the turbulence and away from the vehicle, I should only have a very small amount of vorticity that's maybe just due to the atmospheric turbulence, or ideally close to zero relative to the vorticity in the boundary layer. So your eddy viscosity is really going as your vorticity times the integral scale of turbulence. That's how it's formulated. So let's look at the original paper besides these major equations and kind of dissect it and see how they thought. And here's a paper I pulled online. And this is a work of the United States government, and therefore it is not subject to copyright restrictions in the United States of America. And I always like to point that out in case, because I have people complain to me sometimes that, oh, you know, you're using copyrighted material. So this is just for the intellectual property lawyers, or budding ones. So this was presented in the 16th AIAA Aerosciences meeting, which happens every January. It still happens today. It's called SciTech today. They renamed it And this is a highly cited article that was used in hundreds of CFD codes around the world, and I don't believe they moved it to an official journal article either. So I think that's good advice too for people in academics, is try and move your conference papers to journals, especially today, so you can get appropriate recognition. I think that's a good strategy. So let's kind of go through the paper and highlight a few interesting things. So here's the abstract. I like to dissect these papers and really look at important things, in my perspective at least. And often in the introduction, they put their contribution almost right away. It says, algebraic turbulence model for 2 and 3 dimensions separated flows, which I just noted, is created to avoid the necessity of finding the edge of the boundary layer, which you see is required in the Cebeci-Smith model. Why? To find boundary layer parameters like delta, for instance. And these properties of the model are determined and comparisons are made with experiments for these cases, including shocks and compression corners and transonic airfoils, which I just kind of drew. And those are their validation cases. And they're going to go in there and note some of the deficiencies of their model also. You can see down here it says Harvard-Lomax second author, and there he is. Oh, chief of the computational fluid dynamics branch. And so it's kind of typical in that group to have your branch chief put themselves as the second author of your paper. I guess it's sort of like how your professors here at the university put themselves as second author, huh? Anyway, they have a list of nomenclature, so you can refer to that if you miss any variables, of course. And this is where they really lay out the problem. And I think this paragraph is great. They do it like a problem solution benefit. They say this is the problem in the field, this is our solution, and there's a small benefit statement in there. So it's a great way to kind of open a paper. And they say there's a practical need in aeronautics and other fields for calculating the compressible turbulent separated flows, which Cebeci-Smith also has a lot of problems with, and this paper will also. And that's part of what Johnson and King did in their paper that overcame it. Of course, that's not been yet achieved, but and I should also mention at this time, there's also emergent and known two equation models, but they're too expensive to evaluate with their computers at the time. But even then, some of these models are not satisfactory relative to algebraic models. So they are looking for simple empirical turbulence models that can be run quick for vehicle design. Now they say right away, the objective of this paper is to present results from an algebraic model developed for use in 2 to 3 dimensional Navier-Stokes machine codes. It's based on the original work of Steger for a simple biconvex airfoil. And they talk about the applications of their model, which are also being published in a NASA document. So that's good. Now let's look at their methodology and how they are thinking. Right away, they say this is a 2-layer model in this paragraph. And they use the eddy viscosity approach, just like all these other algebraic models. And since they're in a compressible flow, they have an energy equation, and they are going to approximate their heat transfer as an eddy viscosity over a Prandtl number. So this is the second way of closing the model, that they're going to adding the viscosity of the Prandtl number to eddy viscosity over a turbulent Prandtl number. And those are usually PR 0.7 in practice and PRT of 0.9. Okay. So let's go in and start looking at the equations. So here's your inner model, which I kind of summarized on my summary slides. Eddy viscosity. And they call their crossover coordinate M. This is really M, which I drew in the beginning of the class, and this varies from 0 to infinity. And M occurs where there's that crossover. So imagine you're coding this, because he never really talks about numerical implementation. You can actually evaluate the eddy viscosity, like the inner one, throughout the whole boundary layer. But you know at some point, the eddy viscosity in the outer layer is going to dominate. So what I do when I code this is, because I have way more memory and computational powers, I just calculate the inner and outer eddy viscosity through the whole boundary layer and just take the maximum. I just send them through a maximum function. And then that way I'll recover the eddy viscosity itself. Y is the distance from the wall, of course, and that's pretty easy. So now he goes in once again, and this is a compressible formula like my paper, and he does the Van Dries formulation. So here's that magnitude of omega in the inner layer, just like I showed, and there's the Van Dries form. So this is all just from the form. He defines omega, and here's the non-dimensional distance from the wall for incompressible flow, W equals wall. And then he does the outer viscous formulation. There's viscosity outer. And he defines these things. This is a coefficient. Since it's two coefficients multiplied to each other, you could just reduce that to be one coefficient. This is your wake function, which you can use if you're determining a wake flow. And then this is, again, your intermittency factor. So just like before. So this is all just small modifications of Cebeci-Smith model. He goes on and defines the intermittency function, which is fine. And that's definitely should always be used for any type of turbulent flow. Up here, when you, and this is really the end of the model, just like I summarized in my summarized sheets. This paragraph here is all about wakes, so I just disregard it because we're interested in boundary layers right now. And then he went on, and this part of the paper really caught my eye. And this part of the paper is on transition. And so a lot of this stuff up to here, except for a few small changes like going with vorticity, is pretty standard. But this part here caught my eye because it's about transition. And let's read this whole paragraph, because it's an early transition model that other models didn't incorporate. He said the effective transition in turbulence can be simulated by setting nu t equal to 0 everywhere in the profile, which the maximum tentative computed value in nu t is from the foregoing relations is less than the specified value. So you see, you can always, even if you have a round space closure, you can always set the eddy viscosity to 0, and you should be recovering a laminar flow model. And as the flow progresses, if you have shear, like partial u, partial y, then the eddy viscosity should be increasing. But even if you have a tiny little bit of eddy viscosity, it might be still seen as a laminar flow, because it has very little effect. And so he actually has like a small value of eddy viscosity where he would like trip the flow and trigger it. Alternatively, and that's a way to try and predict transition without setting it empirically in advance. So I suppose the original way is you might have a ball, and I would just say at x equals, I don't know, 2 meters, for instance. I would say nu t is not 0 anymore. And before it, nu t is 0 at that, in this location, as the flow goes downstream. And so then I would just let nu t be non-zero at some point where I know the flow transitions. The nice thing about this model is he's setting like a cutoff value for nu t, and as it increases, then trips flow. And he has something like that in his paper. So anyway, these are all the equations, and he just took these and integrated them with the laminar existing Navier-Stokes solver for steady flows and for a boundary layer formulation. And then he runs it against a number of flows, and you're faced with calibration. And here he's identified all the coefficients that are unknown and how he set them to be constants. Now you can always go in and make them functions, right? So I could always go in and make something like A plus is 26, but you know that A plus is not a constant. That should vary with pressure gradient. So I could easily change, say, A plus to be a function of pressure gradients, no problem. But right now he's keeping them all constant, and that's a sign that it's a good predictive model, because you wouldn't want to recalibrate your coefficients for different flows. That wouldn't make a lot of sense. So a lot of these are standard from before, like this one. A plus is 26, PR, PRT. These are measurements. The wake function, that's a measurement. And I'm honestly not completely sure about some of the other ones. But what he would do is set some of these to like what we believe to be known values based on other studies or analytics, and then calibrate the others with experiments. and for a single flat plate boundary layer at high Reynolds number. And then he takes those coefficients frozen from the flat plate flow and applies them to more complicated flows. And if it's a good model, I would still be able to predict against experiments from more complicated flows and have small error. Now, this is where he takes a little bit of a philosophical turn, and we've been mostly talking about boundary layers. And there's also another set of type of equations called thin layer approximations. And I think it's not too important in the context of this paper today, but it turns out that there's certain advantages for like having thin layer approximations versus others. And this is where he talks about the difference between thin layer approximations and boundary layer approximations. And it's just basically about different terms being more dominant than others. In contemporary CFD, I don't think that's terribly important at all, because you're not solving boundary layer equations anyway, you're solving a general set of Rand's equations. But they argue that as you go at higher speeds, that doesn't make a difference anyway. Another thing when I was reviewing this paper, because it's pretty interesting, is that he implied something about LES. So not only did this paper have some of the first transitional type models for eddy viscosity model, which was predictive, he's also looking at a small LES thing. And I saw this in here. He says the equations have to be solved in a thin layer approximation are based on a time average or subgrid scale model of the Navier-Stokes equations. And I hope that at the end of this class, before we do some of our, kind of like quick presentations of what you've looked in your term paper, that we'll talk about some of the LES philosophy and subgrid scale models. So that'll come back. Okay, so anyway, he formulates all this, and he did put a lot of his, most of his predictions in NASA technical note, which is on NTRS today. Let's look at some of these major predictions. So first he looks at flat plates. And before we get into that, let's look at the timing. So shock wave incident on flat plate, flow over compression corner, transonic airfoils. This is his solver convergence, number of the steps. This is his grid points. You see it's pretty limited. He only had 64 by 36 and 77 by 36 grid points, so it's very tiny. And he's using a $5 million computer to solve that. Now think about your computer project now. I mean, some of you have 1,000 grid points in one direction, and maybe 400 or 500 in the other. So, that's nothing for a contemporary laptop to do. So it's quite luxurious. Here's the CD 7600. So these are in seconds. So this is on the order of 30 minutes. So he was using his $5 million machine for 30 minutes to find one result from these codes. Anyway, that gives you an idea of the computer power. Okay, so let's look at some of these flat plate cases. So this is really a transitional test. And it's by an experiment. So the experiments are these dots, and their predictions are called calculations. Here's skin friction, and then this is increasing REX. And so when you have small value of REX, you would expect to be laminar. As I increase it, remember REX goes as the distance along the plate. I should transition from laminar to transitional flow, and then transitional flow to turbulent flow. So if you look in here, where's the transition? Right in here. And, in his writing, he just says, this is like good agreement, which isn't very quantitative, which is something I enjoy. Mach 1.5 and 2.85 incoming flow. And, at the time, given the quality of the experiments, this is a very, very good prediction. It lacks error bars, though, which would have been nice. So there's one of your first transitional predictions of a closure at high Mach number. And it did predict relatively good. So here might be the first transitional point, and this is the experiment. Well, this is experimental. This is maybe the tip of the prediction transition. And the second case, he compared, I believe, momentum thickness. And once again, this is REX times 10 to the negative fifth or 6 or so. And that's, remember, that's just going as the x direction along the plate. Everything's being held constant except x. So you can kind of think of this as like the x direction. And lower Mach numbers, he calculated the correct trend. Higher Mach numbers, then, unfortunately, is momentum thickness is growing at the wrong rate, which is too bad, but it's an honest prediction. Lower Mach numbers are going to work better. As you approach higher and higher speed, you're getting the hypersonic regimes, Mach 4 or 5. This whole model is, of course, going to fall apart. But it should work well over a subsonic range through low supersonic speed. Okay, then they looked at shock wave incidence, flat plate boundary layers. Let's look at this one quickly. And down here, there's a little diagram of what's happening. You have a Mach 3 flow coming from left to right. Here's a wall, right? And a shock wave is dealt by the little wedge here. And when you have your little wedge in the wind tunnel flow, a shock wave is becoming left running, and it hits the wall and it bounces back off. So this is a turbulent flow. It's unsteady. And there's a little issue with this now. Because you remember in like compressible flow class, when we said, oh, we have a 2D flow, you know, maybe we have the Euler equations, and we just have a nice perfect reflection. But there's a turbulent boundary layer, and when a shock wave, often oblique, hits a supersonic turbulent boundary layer, it's going to reflect off, just like in the inviscid case, but sometimes a recirculation bubble will form at the wall. And that's bad, especially for flight vehicles, because you have very high heat transfer rates into the wall. And so we want to be able to predict them, predict those heat transfer rates, and hope that we can design a vehicle where our wings are not melting off. Like in the space shuttle leading edges, we had very, very, we had like these tiles, right, to try and absorb the heat from the shock waves hitting the wings. Anyway, this is just a simpler experiment. So here's the experiment with the reference, and he did 2 calculations now. He did the first calculation with the method just described. So there's our experiments, are these points, and the x-axis is x on the wall. It's normalized by boundary layer thickness, I believe, before the shock impingement. And the y-axis here is skin friction. And I think it's very interesting. We can learn a lot of physics from just looking at these things. And so in here, this is roughly location of first shock and roughly the location of the second shock. And you're trying to measure this near the wall. But you might say, okay, there's shocks. Why isn't it like a discontinuous function or something, or sharper? Well, you have a turbulent boundary layer there. Remember, it's not supersonic at the wall. You have subsonic flow at the wall, even though the whole flow in the interior of, say, the duct is supersonic. So the calculation, his prediction is the line, and I guess it has good agreement, but he doesn't give me any quantitative information about air, which was a lot harder to do back then. And then he has another prediction called law of the wall prediction. And does anyone want to take a guess at what that means? You know what the law of the wall is, right? It's some assumed form of the boundary layer near the wall. Okay, well, that means that I'm just taking an assumed form of the solution, which is like y plus equals u plus connected to a log layer out to y plus a 50. And I match that with the numerical solution. So I assume that there's a solution at the wall that's like a log law wall, and then outside of that, I'm basically matching my numerical solution with. So here's a follow-up question. Why would I want to go to all that trouble? It's a beautiful day outside. Yesterday we had rain, so now it's a beautiful day, so now we're inside talking about turbulence theory and CFD. Well, the clue is most of your grid points are near the wall. So if I know the solution near the wall, I could just eliminate all those grid points entirely and have my first grid point truly at y plus a 50. Because I know I'm assuming what the solution is near the wall. And most of my grid points are, of course, in that region because I want to resolve the high gradient. So through this approach, I have immense computational savings. And that's not computer limited because today we have wall modeled large eddy simulation. And when you hear wall-modeled large eddy simulation for these unsteady supercomputing simulations today, they're also assuming some form of the boundary layer near the wall. So you see this idea has stood the test of time. Let's look at another graph. This one's surface pressure. So this is pressure on the wall, newtons per meter squared. That makes sense. And there's your x direction. And you can kind of see where the two shock locations are going to be in these locations. Not predictive. Not predictive at all. Of course, he has the initial condition correctly, but that's something that's super easy to calculate. Within the separation region, this little separation bubble where you have flow reversal at the wall, not so easy. Okay, let's look at a few others. He notes in here that he mispredicted separation, and that's where Johnson and King are going to come up. This paragraph down here, he explains all the law of the wall stuff if you want to read about that. And now let's look at a third experiment. Separated flow over a compression corner. So what is a compression corner, you might ask? Well, it's some flow like this. And this is going to compress the flow in here, and it's going to come in and form a shock wave. So the flow is going this way. This is a shock. And this is, of course, P2 is greater than P1. This is P1. Right, so a shock wave forms, and that's shown in this tiny little diagram down here. The angle of the wall, this is the wall, it's turning at, I think, what was it? 24 degrees, which is pretty steep. Definitely not a hypersonic vehicle. And we took measurements along the wall. So you can see in supersonic vehicles, this is pretty important because you have if you ever want to have your vehicle have any thickness, you have to have some kind of compression corners along the vehicle to have a fuselage of non-zero thickness. So once again, he has looked at these experiments and then looked at calculations. And I love this experiment because it was led by a guy named Gary Settles in his early work. And Gary Settles was one of my professors at Penn State Aerospace. So it always kind of hits home when you see one of your advisors' work being used for benchmarking. And in here I wanted to highlight the sentence. He said they calculated the region of reverse flow is too large and the predicted retachment points differ somewhat more from the boundary layer thickness from the experiment. So you see he's very critical of his own model and what's wrong with it. So those are just things he's identifying that even though this model is more advanced and better than Cebeci-Smith in a lot of respects, unfortunately it still has a lot of things to be desired. Experiments, once again, are these dots. This is pressure on the wall relative to the ambient pressure. Lines are predictions. And you can see if this is 1, so this is P equals P atmosphere. You can see up here, this distance is about a half an atmosphere. That's 50 kilopascals. That's a huge error. And I wouldn't feel like it's an acceptable prediction if I was designing a vehicle. Let's look at another compression corner case. This is skin friction. Skin friction is very hard to predict. It contributes a large amount to drag and your drag coefficient, and post-shock compression corner, the error is very large. When you get downstream, it gets better. A few other quick graphs just to mention. Here's the transonic airfoil case. So a lot of flight vehicles are flying the transonic regime. Transonic airfoil is like where we have an airfoil, and the Mach number is going to be the order of 0.85 and a little bit higher, maybe 0.95 in that range for thin airfoils. And what happens, of course, is you get shocks appearing on the airfoil if it's symmetric, and then there's a separation with a turbulent wake. So you see that he had different factors, and this is a boundary layer, streamlines. You had different factors, right, for boundary layers versus wakes. So another thing, if you just took a paper like this from the theoreticians at NASA Ames and said, well, how do I implement that in a code? Because I have a flow with boundary layers and wakes. So that's a huge issue. And if you're using a marching code, it might be easier because you can look for where the flow separates. Or if you have an iterative nonlinear solver, which is what they were using, then you have to have some way to detect it as you're converging and then switch on or off the F-wake functions. So that's a whole another level of empiricism, which is left up to you as the programmer. And I suppose that's why a lot of these CFD codes in early aerospace companies were really secretive, because they were trade secrets in terms of flow prediction. So anyway, let's look at some of the results for this transonic airfoil. And I believe that this axis is y plus. So here's the y plus distance, non-dimensional, and then here's u plus. And this is near the leading edge. So if you go look at this airfoil, these predictions are up here near the leading edge. So things are pretty well behaved, but you can see this doesn't look like a typical composite profile at all. In fact, I don't see a log law at all. Why is that? Because he's near the leading edge and the flow is not fully turbulent yet. So his transitional solver seems to be working. And the proof is relative to measurement, because that's what we believe to be the truth in this case. And the predictions and measurements are rather good. And here's the exact location. He's at a 1% chord length on the upper surface, so C is chord. All right, and that's just the length of the airfoil for those of you who aren't familiar with airfoil coordinate. Okay, now let's go the trailing edge. So here's the trailing edge of the airfoil. This is at x over c 80%, right there. And let's look at the profile of u plus versus y plus. And we've seen a lot of these in this class. You should start looking at them and say, this looks like a composite profile. Right away, I know that. I'm feeling good about my turbulent prediction with this model. It makes me happy. So here's y plus u plus 1. You see, he didn't even get near the wall. His first prediction is about y plus about 8. That's his closest grid point to the wall. That's all he can afford with his $5 million computer. And you can easily afford to get y plus less than 1 in your code if you want, but it's overkill. And then we say, okay, well, there's something like this. Y plus is u plus. Here's the log layer, and here's the coal outer wake region. So this is a log layer, and this is what I call the outer, or I like to call coal wake, because that's paper reviewed and theory where it comes from. So that looks great. That's at 80% x over c. Awesome. And that's post-shock. So from the compression corner case, he had good results post-shock and pre-shock, and you can see that's somewhat the case here too. He doesn't show a shocked prediction or location near the shock. But anyway, there's let's see here. We got a boundular parameter and oh yeah, here's a boundular thickness, delta star. So you see they've extracted profiles along this airfoil of a probe, and it looks really good. So everything checks out there. That makes me happy. Okay, let's see here. Just going down, a lot of the people in the turbulence community are going to want to dissect a lot of the particular things. And here is a plot, since he has the data, of all the turbulent velocity and length scales. And so you can see these are the terms which you see in the modeling parameters along x over c of the airfoil. So he extracted these parameters from his turbulent boundular simulation and tried to compare them with experimental estimates. And that's one of the beauties of CFD, is you have all the data. And since you know the equations you solved, you can reevaluate terms in the equations and try and match up with experiment. And this took an incredible amount of work, and part of the reason he did this is because all these quantities were found from the flow solution itself and not like estimated before you started your flow solver like Cebeci-Smith. And it agreed with the experimental data for a transonic airfoil. So that was a huge accomplishment. A few more notes. We'll just look at the conclusion and we'll finish up this model, and then we'll look at the next one, which overcame some of its problems. So let's just look at the conclusion quick. And once again, he restates what he did in like one summary sentence. Algebraic eddy viscosity model has been developed that has several worthwhile properties. And he notes what those are. The first one, his first accomplishment, he's bragging, he's talking about facts. It eliminates the need for finding the edge of the boundary layer and removes one of the sources of arbitrariness and potential error that was present in the previous models, in particular Cebeci-Smith, which was the dominant model. Another thing, someone else in the Air Force, this isn't my writing, this is some Air Force reviewer's writing from where I got the paper. He said, comparisons with measurements from 2 experiments show agreement in the prediction of separation and retachment points within 1 boundular thickness, which is really small. And that's, of course, good. So he summarized what he did. He points out his major findings in the conclusion, which I think is a good strategy for writing papers when you write your papers. And then he goes on and he's critical of himself. And it's always hard to be critical of your own work in a paper, right? Nobody likes to go out and say, I don't know, some flaw in their character or something. But that's important to do in scientific writing. It's important to be transparent, open, and honest. And this is where the problems are. Problems. And I love reading papers like this because they've just made my job easy as a researcher. Because he's saying, these are the problems I have with this new model. And I say, wow, maybe if I have an idea to come over some of these problems, I can take his model and overcome them. I can write a new paper or maybe get a cool research grant to support one of my students. So that's something you can look for when you read 2022 literature. But let's look at the problems he noted. He said the extent to which the thin layer approximation is applicable to the presence of large shock-induced separation of airfoils neither further investigation. So he was using a little bit different form of the equations. It's not going to make too much of a difference today. But three-dimensional flows are being pursued. So you really looked at, these are all three-dimensional flows, of course. But he's only looking at two-dimensional forms. And thin layer approximation, he said use of the law of the wall boundary conditions avoided high computational expense and often found good results. And that's still being used today in LES and also some RAND solvers if you want to save things. So a lot of that has already been done. But one of the things that this model has problems with, as you can see in the simple case of compression corner and shock on plate, is predicting the region of separation. And why is that? And I think one of the clues is it's like a one-point model. It means the model has no memory of what happened upstream and downstream. You can see the closure always involves just some point and no other points around it. There's no differential equation to track the differences of turbulence in the boundary layer, like, say, turbulent kinetic energy. And this is where Johnson and King came in and said, we're going to try and track a turbulence statistics with a simple differential equation and create what we call the first half equation model. And that's what we're going to talk after the break, and we'll see you then.